Well, okay, nice. So, we'll start with some course logistics. We're going to move, we had the exam on the schedule for Friday, tentatively, but we need to cover computational complexity, which is really difficult to fit into 50 minutes and do it the way it needs to be done. So I need to be able to spread that between today and Wednesday. And so I didn't want to put your exam, I wanted to do a review, and I don't want to put an exam on a Monday. So next Wednesday is when we will have the exam, and we'll have the review on Monday. Yes?
So is trees going to be on the exam?
Okay, yes, great question. Trees will not be on the exam. So on Friday, we will probably do kind of just loose ends on everything and then a little bit of trees. But I won't be like going into depth on trees and because you don't need to know it for the exam. So we'll pick it up with trees after the exam. Yeah. And so we'll do a review of everything that's going to be on the exam before the exam, but it will just be linked list, stacks, queues, and computational complexity. And then maybe one or two of those basic C++ kinds of questions, but really probably just one of those.
So is there anything besides the review we can use to prepare for the exam?
Yes, you can use the lectures, the slides. That's all the same content that will be on the exam. During the review, I will give you a summary sheet that condenses everything kind of into 1 or 2 pages that should be helpful to you, and I'll give you practice questions. Yeah. So practice questions are probably the best practice for the exam. Okay. Any other questions about logistics things, everybody? Good, okay. So last time we talked about stacks and queues, kind of briefly. They're very basic data structures, but essential data structures. So just to refresh you on that, a stack is a collection of elements, whatever kind of data you want. And it follows the principle of last in, first out. And so you can think of it as a stack of physical things in the world, right? If you stack paper one on top of another, you always take the one on top off. Don't reach underneath, that's cheating. And that's the principle of the stack. And it doesn't matter how you implement it, right? So we talked about you could implement it as an array if you want, where you just keep track of the index of the bottom and top of the stack, or you could implement it using a linked structure like we did with a linked list. But the main thing being that it's a collection that has that last in, first out property. We also talked about queues, which are kind of the opposite in that they have the first in, first out property. Just like a queue in the world where you would line up in order waiting for something, like a print queue or a queue of tasks to run on a CPU. Queues are everywhere. And again, it doesn't matter how you implement a queue. You can implement it as an array, or you can implement it with a linked structure as long as it follows that principle of first in, first out. And later we'll look at priority queues, which change that structure a little bit in that you can have items in the queue that are given certain priorities that are higher than others that actually change their ordering and how they're removed from the queue. And so with the stack, we said that you either push or pop elements onto or off of the stack. And with a queue, we say in queue or dequeue. And you may also see push and pop used for a queue as well. But just know that those are all kind of synonymous. They mean the same thing. So today, I want to start thinking about computational complexity. And I think, have most of you had some mention of big O in your previous courses? Okay, yeah. So we'll come at it from a naive approach. So what you know from your other courses, you'll be able to fill in a little ahead of time as we go as to where we're headed. But it's nice to kind of think of it just on a basic level to start with, not to get too deeply into it. So we'll do more of the Like the mathematical side of it, the notational side of it, we'll do that on Wednesday. Today we're just going to think about kind of how we should approach this and why it's important. And so we'll start with a really basic question, and that's, what is an algorithm? Anybody have a... Yeah.
Series of steps to take to do a certain outcome.
Yeah. So series of steps for solving a problem. So kind of like the go-to example that I've always heard, at least, is like a recipe for cooking something, right? Is an algorithm in a sense that it's going to specify like things you need, so some inputs, what you do with them, and has some output, right? So, and that's something that we're familiar with as computer scientists or engineers or anybody who's programming something or designing these processes, is that we have this basic idea of some kind of input, a box, whether we can see in it or not, and then some kind of output, right? And one thing about an algorithm, and we talk about it in terms of computational complexity, is that we want to separate out the implementation of an algorithm and the algorithm itself. And so what I mean by that is you can implement the same algorithm in many different ways. It may just be small details, and we'll look at some examples, but the implementation can depend on a lot of things. It can depend on the language you're using, it can depend on your own preferences and choices, and it can still implement a broader abstract algorithm. So in the sense of like, if we have an algorithm that is sorting or searching or doing something like that, there are a lot of ways to do that. And even within very specific searches or sorts, there are multiple ways to implement those specific sorts and searches. So a basic example of an algorithm could be something as simple as finding an element in an array. So you've got an array, let's just say of integers, and you just want to go through the array and see if an integer that you have is in that array. So it's basic search. And so when we look at complexity, we will just use kind of whatever syntax and code is convenient. It will use a lot of pseudocode, so it doesn't need to actually compile into a language. We don't really care about language details so much. So I'll be showing you things that are a mix of different languages, and some of them will actually not be any necessarily valid language, but you'll be able to read it as having conditionals, having assignment statements, that kind of thing. So just for this simple example, we've got this idea of finding an element in an array. And I've got two versions of this code here. They're only slightly different. Which one is better?
The second one.
Okay, why?
I don't really have an answer. It just looked like it should be right.
One less variable.
Okay. Yeah.
Might be a little less readable.
So let's think about the first one here. What we're doing is we're coming through this array. So this function would have an array passed in. We have a target value we're looking for, right? We set up this variable that says how we found it or not. And then we're going to loop through the array, checking each element to see if it's the value. If we find it, we're going to mark this as true. And then we're going to keep looping through the array. And then at the end, we'll return if we found it or not. In this one, we'll just do it a little bit differently. We'll come in, we'll start looping through the array. As soon as we find the value, we're going to return. We're not going to look at the rest of the array. So,
It's more efficient.
maybe. Yeah, it is. If you look at it in terms of just operations and runtime, right? This, in most cases, will be faster. When will it not be faster? When will they be the same?
It's the last true.
So at the end of it, or if it's not in there at all, right? So you have to go through the whole array either way, right? So this is going to be an important thing to think about, and this can be a little bit tricky at times when it's not such a simple example. But when we start to think about computational complexity and what we care about, these two are the same, because what we're always going to care about is the worst case. So we're always going to care about the case when it's not in the array at all. And so we want to come up with a way of evaluating any kind of algorithm, not something so simple even, where we can kind of cut through things like these little differences. Now, these little differences can matter a lot in the real world, kind of on average, depending on like your data set and what your algorithm does. This could actually save you a lot of compute cycles. It could actually be a lot faster. But it depends on what you're searching for and the distribution of that data. So that becomes a trickier thing to actually calculate and know. So generally with computational complexity, we will care about the worst case always. So it will always be the case where we don't have the element in the array, where we have to look through the whole thing. So another basic question, what would be a good algorithm? Characteristics of a good algorithm.
One that's efficient but takes less steps.
Okay. Other ideas?
Doesn't do unnecessary work.
Doesn't do anything unnecessary? Has a great name, maybe? I don't know.
Not really east across the street.
That would be good. Yeah. So, I mean, you could see, you know where this is going, right? What's a good algorithm? Well, first of all, it has to actually solve the problem that we want to solve. It would be nice if it did it in an elegant way, right? If it was kind of a clean approach to the problem, but it doesn't really matter in terms of the complexity. But most of all, what we want to do is we want to solve the problem and we want to optimize on some characteristics that we're interested in. And usually those come down to two things for us, and that's either time to solve or space to solve. Now we'll look mostly at time in this class, and you'll find that most computational complexity will focus on time, or you'll quickly translate space over to time. But it's good to remember that that is a choice, right? And you could choose other things. And so space sometimes is the priority versus the time that it actually takes. It just depends on the algorithm. Okay, so what makes an algorithm efficient? That's the next question. Less operations, yeah.
If it's a problem, then optimizes work too.
Yeah. So to answer about efficiency, we can kind of start to think about comparing algorithms, right? Essentially, what the most efficient algorithm is going to be the one that we know to do it the fastest, or to do it with the least amount of space, if that's what you're optimizing on. So in general, if we kind of think of it in higher level terms, we can say it solves the problem using the fewest resources and in the smallest amount of time. You could think of time as being a resource itself. So you could just sum this up as using the fewest resources. But generally for us, time is that resource that we care about a lot. So another thing is when we think about an efficient algorithm, we really have to think about the case of very large input sizes. So if we compare algorithms and we only look at, in the domain, what's considered a small input size, right? So like say we're searching for something in an array and we only consider arrays of, 100,000 elements. We never go into like 10 million or something like that. We can arrive at conditions where two algorithms perform either the same or one better than the other for small numbers in the input. And when I'm talking about input, generally for input, we're talking about a size of a data set. Occasionally we're not. Occasionally we're computing something. But whenever we do this, at the beginning, when we just have a few elements, a relatively small amount, some algorithms can actually outperform others, but as that number increases, then one algorithm becomes much worse than the other. And so that is another kind of counterintuitive thing that you'll see at times when you're asked to analyze an algorithm and its complexity, is that if you just think about the practical low cases, or if you just experimentally test those cases with just a few things, it can look like they're either all very fast, all the same, or it can even look like one that is actually not the overall most efficient is. So, and that's just what's said here, is that we generally care about performance on very large data sets when we're thinking about complexity overall and when we're looking at that worst case scenario. So that's not to say, though, that practically speaking, if you, in our made-up example of like only 10,000 elements in an array, if that's all you ever needed to do and solve your problem, well, you should probably pick the one that on average is the fastest at doing that, even if it's not the best in terms of worst case performance. So that's a more practical side of this that sometimes can get lost. Another question that comes up is, does efficiency still matter, right? So kind of when field of computer science starts, right, and before that, discrete structures and math and thinking about computational operations, our resources were, a lot less than they are now, right? So today, you can just throw more hardware at it. Every simple program is like a bloated Electron app that's got 4 gigs of who knows what, and is depending on modern OSs to like compress memory and offload things and do all of that. And so it is a reasonable question to say, like, for us today writing code, or if we're going into a career where that's part of it, will this ever matter? Like, will you ever need to think about this? And the answer is yeah, sometimes. Maybe not a lot, but at least a little. Because there are still huge problems, and there is a growing amount of data, right? We produce more and more data all the time, and we're all very interested in doing things with that data, right? So, the biggest thing right now being machine learning applications, right? AI applications where you have huge data sets, right? And you're needing to do computation over those data sets efficiently. And so it definitely matters when it comes to things like that. So, yeah, it matters always. And it doesn't look like there's an end to that in sight in terms of data increasing and the need to process it and do something with it increasing. Okay, so let's talk about measuring efficiency. And we're going to kind of go through a few different ways of how we might do that. So just kind of a naive approach that we could take, right? Say we have our algorithm, right? And we've written it in whatever language we want. We've got it running on our machine, whatever our machine is. What we can do is we could just time it, right? We could be like scientists, like computer science will be the scientists in computer science. I'll let you think about if computer science is science or not later. So. But that would be that makes sense, right? Like, you've got an algorithm, you're just going to run it, say we start at this time, we end at this time, how long did it take? You could do this with different algorithms that do the same thing. You could compare them. You could do this, probably more importantly, if you were going to do this, you would want to run this on increasing input sizes, right? So how much time does it take on 100 elements versus 10,000 elements versus 1,000,000 elements? And then you want to quantify that relationship between the input size and the runtime. That's our goal here. So can anybody see the problems with using this as an approach to analyze efficiency?
It looks like it's gonna take a lot of time.
Yeah.
Like analyzing the trends between input sizes, you could have 100 input sizes, or measuring the amount of time it takes to run. Like, it's gonna take different amounts of time to run depending on how much you're running.
Right. And how much RAM does my laptop have in it, right? If I care about really big input sizes, I might need to test with something more than I have the resources to try it on, right?
So therefore, you're not a scientist.
Sadly, no. But maybe. There's hope. You can all be a scientist. So this isn't horrible, right? This isn't the worst thing in the world you could do. And it certainly makes sense if you have like an application and you're like, I need this thing to happen. I'm going to try this code. we're going to see what the output is. We know the constraints, right? We know we're only ever going to, fly from Earth to the moon, right? We don't have to worry about Mars or whatever. Maybe it makes sense. I don't recommend that for space flight, but it's not a bad idea. But there are some shortcomings here, and these are honestly, this makes a lot more sense when you think about doing this analysis with limited hardware resources, right? So again, we are pretty lucky today, pretty privileged to have the computation resources that we have. But if you imagine a time where you didn't have that, or you imagine a very large data set where you need, more than the AWS cloud to do something with it, then we start to see shortcomings, right? So the first major shortcoming is that kind of unimportant implementation details are going to affect the amount of time it takes for something to run, right? And it may not be a lot, it may be a lot, it just depends, right? This could be things like the language you're using may optimize certain operations versus others, the machine you're on, the OS you're using, any of these factors could cause things to play out differently, right? And maybe that's okay if you can compare two algorithms in the same exact environment. You could at least answer that question. But in general, this constrains you. Because these details will contribute to the runtime. And it's hard to tease them apart, right? There's a lot more than you can even think of really on the surface, right? And it's always that one like weird thing. If you've ever written software and it gets large enough to where you're trying to like hunt down bottlenecks in it, right? You're trying to see where am I losing, compute cycles. So this happens a lot in, it's like I work in robotics, right? Things happen pretty quickly, usually like if you're doing sensory input or something, right? So, milliseconds are a lot of time. And so if you're suddenly losing, like tens of milliseconds somewhere, you've got to find it. And you've got to see what's going on. And sometimes those are the most like non-intuitive things. It can be something like deep in the stack of hardware or software, and it can be an obscure bug or an edge case or whatever. And so those things have an impact, and it's very hard, like from a high-level analysis perspective, to account for those. So the other obvious thing is that the hardware you're running it on has an impact. Now, you could say, well, we can normalize that, right? We could, in a statistical analysis, we can control and take into account like the specs of the hardware or something like that. But in general, this is constraining if we want to just think about and look at algorithms and be able to compare them without having to deal with all of these factors. This becomes a lot. This becomes a whole job in itself. And then the last thing is that, of course, for very large inputs, we may not have the system that we would need, or we may just not have access to it, more likely. And so we want a way where we can still say something about an algorithm and its performance without ever running it. So let's try a different approach. What if we just counted things? So what if we just looked at our code, and maybe we can agree, like, we'll count certain things that happen in code. There's only so many things that happen, right? I mean, like if you choose a processor, like, probably not an Intel one, maybe like an ARM processor or something, look up like the instruction set for it, right? The piece of hardware does so many things. They're listed out, right? So let's not even think that detailed, though. Let's just think about like high-level code. So things we do in code, we assign things, we save things, we retrieve things. We might do math operations where we, add, multiply, any of the others. And we do comparisons. Comparisons are pretty important too. So if we could all agree on a subset of either, we can call them fundamental operations or primitive operations, and we'll say, okay, each one of these counts as like 1, right? So every time you add something, we add 1 to the count. Every time you compare something, we add 1 to the count. And then we could just count the number of operations as a function of the input. And we would come up with a formula for any piece of code, and it would tell us how many operations, based on the size of the input, you would have. Anybody think about why there might be some shortcomings with this approach.
Different compiler with different instruction optimization.
Right. So we mentioned at the beginning that you can implement things in different ways, right? The same algorithm can be implemented in slightly different ways. And if we're looking at primitive or fundamental operations, there's a good chance, like the two array searches we looked at, right? They have different numbers of primitive operations. But we know that they're essentially the same in the worst case. So we this helps solve one problem. So it's not, all bad, but it doesn't completely solve it because it doesn't allow us to ignore some extraneous factors that don't really matter, some of the implementation details. So let's try to do this though, because this is somewhat helpful. So we're going to just go through this little simple code, and all this does is return the wrong thing. Huh. I'm going to fix that. There we go. That makes more sense. Okay. So we've just got this function here. We're going to pass in an array, and the job of the function is just to add up all the numbers in our array. We'll say it's an array of integers, right? And so we'll assume that we'll say our array A has a length of n, right? And so all we do is we'll set up a sum, we'll go through, we'll add to sum, and then we'll return sum, right?
So that's like if you want to add, like in Delphi, for my program like 1 and 2, we had to add up like 1 through 100 and display the value.
Mm-hmm.
This would be like a case like that.
You could do it this way. This would be like, say you've got an arbitrary array of numbers, you don't know what they are, and it's just like, add them up, what's the total of this array? So you can imagine like the practical example, like just like a spreadsheet, right? Like you've got a column of numbers, you highlight it, and you say sum, same thing. So if we're going to count operations, we could say, okay, we create sum, and we set it equal to 0. Let's just call that one operation. We could debate if that's 1 or 2 or whatever, but we'll call it 1. Then, for each time we go through the loop, we're going to have a variable for the index, so we're going to call that an operation as well, just to increment that variable and store it. Here, we're going to both access a value and add, so I'm going to call it 2 operations. This isn't super important, right? Again, we could decide what's an operation and what's not. And then we'll say returning it is one operation as well. So if we want to count up these operations, right, we can do it this way. So this first operation, this only happens once for the whole thing, right? So we'll just put it here. Now this for loop, incrementing that index, how many times does that happen?
As many as in the array.
Yeah, so n times, right? Same thing here, right? Within the loop, it's going to execute n times. So it's 3n, and then we return 1. So we can come up with something like this, right? We can say number of operations is 3n plus 2 for this function. And that's honestly pretty good. It characterizes it well. You can plug in whatever you want for n and get a number. And it's not dependent on any specific hardware or implementation environment. So let's talk about what's good and bad about that. So no hardware requirement. We can do it for large input sizes. We don't even have to run it on anything. But the downside is that implementation details still matter. So we're still counting things that overall, they're unimportant. We don't really care about them. So what we need to do is try to isolate the algorithm from implementation details. So what are some of those details that don't matter here? The things that happen once don't matter. So when we look at this, the term that what we'll call a dominant term is this 3n, right? Plus 2, who cares about that? Especially as n gets bigger and bigger. It doesn't really matter. So how can we measure efficiency in this way that doesn't look at these implementation details, that ignores them? So we'll call this order of growth, is what we're looking at. And we're trying to classify things into kind of families of growth based on their input size. So everything is based on relating time to the size of the input. Could be space, but we'll say time for now. And we're going to just try to get rid of those implementation details. So we want to ignore anything that's unaffected by input size, essentially, right? So like in our function, a few of those things, it didn't matter how big the array was, right? We always had a sum variable, and we always returned a sum variable. It's just not important in terms of the input. So part of this analysis is deciding what is the input that matters, right? Because usually we have more than one input to something. And so it's obvious in cases like this, well, that array matters. How big is the array that I'm searching through? It's not always obvious in more complicated things. So we also want to look at conditions where the input is large, and we want to always measure in terms of the input. So here's kind of the question, how long does this take? And we could go through and we could do this with our counting operations and decide. But what's the most important factor here?
That it returns a value.
It does return a value. In terms of like how long it takes, though, what dictates how long it takes?
Length of the array.
Yeah, the length of the array. So when we do these analyses of algorithms in terms of their complexity, we generally we can look at three different things, okay? So the first one is what we call best case, right? This is generally a waste of our time and unimportant because in the best case, the answer is just like the first thing you get to, right? Like your element is the first element in the array and you're done. It just took you one operation. So you can say that's constant time. It doesn't really help us to know that because kind of that's like universal, right? Any algorithm you look at, you can say, well, in the best case, it only does one operation or whatever. Average case, which we've talked about a little bit, is probably something that matters in a practical sense quite a bit. But it's also one of the hardest things to characterize for some things. So one of the reasons is that it depends so much on the possible input space and the distribution of inputs. And you can think about, so like, searching through that simple array, okay, whatever. Think about if you had to sort that array, you can already imagine you would need to represent each possible order of the array at the beginning, right? And that kind of explodes in space. So you can sample, you can do a lot of things to characterize that. But for the most part, we're going to focus on worst case. And that's because we want to be able to offer performance guarantees. We want to be able to compare algorithms and say in the worst case what each will do. So best case, best conditions, it's really not useful. In the example of searching for the element in the array, it's the first element, and just by definition, this is kind of a trivial case. Average case, how long does it take usually? Usually is what makes this important in practical terms, because that's what matters to people actually using a system, right? So it's a good metric, it's an important metric. And you can imagine for the array, maybe we don't have to try every possible ordering or whatever. We could just sample and be confident about our distribution. It just takes more effort to do this. So this is an extra set of steps. And it can be very difficult in complicated scenarios. So average case. Now worst case. this is what we'll focus on. So we want to come up with an upper bound. So for any algorithm that we're looking at, right, we need to think about it. It's kind of good just to like, if you're given the algorithm, what is it supposed to do, right? How does it do it? And think about what is the worst possible route that could happen logically, right? So if we're searching for an element in the array, well, the worst possible thing is that the element's not in the array, right? Because we won't know unless we look at every element in the array. And that's the most work we can do. So this is what we care the most about. And again, order of growth, right? We want to describe the growth of the runtime as a factor of input size always. And so what we'll be doing is we'll be plotting out a curve, basically, right? And you can think of like on the x-axis having your input size, and on the y-axis having how much time or how many resources it takes. And what we'll find is that there are different curves that exist for different algorithms, right? And different classes of curve. And so we'll call those orders of growth. And so a practical question you might ask is like, if I double the input on whatever algorithm, how does that affect its runtime? Does it double the runtime? Does it quadruple it? Is it some exponential, right? Because it matters quite a bit in terms of will this ever, return or end. So with order of growth, we want to put this upper bound on the function. And we don't want to focus on the exact runtime. We don't care about that. We care about the most dominant term, the part of the algorithm that is taking the most time, always. And so that makes this kind of good. That helps us cut through a lot of things. And it turns out to be what really matters. So we'll talk about big O notation a little bit. We'll get into it more next time. But essentially, big O notation is what we use to describe the worst case runtime. Pronounced big O and written with an uppercase O. And in this case, like if you have a big O of n, that's how you write big O of n. So that's a linear function, right? It just takes the amount of time that's proportional directly to the input. So things that we ignore when we do big O, any kind of constant factors. So if there is, an operation that takes place like 5 times, but that's all, it's not affected by the input, we ignore that. If, let's say we have an algorithm that has an operation that takes place n squared times, right? But it also has an operation in it that takes place n times. So like, if we were counting operations, our formula would be something like the runtime equals n squared plus n. In that case, we don't care about the n. We just care about n squared because it is the dominant term when we go to larger and larger n's. So that's what we're always focused on, is pushing n very large and seeing what happens. So to give you some examples, so these first few will be what we call order of n squared, right? And let's just say these are counting functions, okay? And like this describes our algorithm, right? So in these two cases, you can see it doesn't matter. Here, we've got a +2, that's constant, that doesn't matter. We've got 2n, that could matter, except that we have an n squared, which is a higher term. So it's the dominant term. And so that's all we'll take away from that. And the same follows for the next one. And we can do this through all of these different classes. So if we say have a term, like we have this representing our function, where we have log n plus 4, the highest one is n. And so order n is what we'll come up with there. And so you can see there are a few other classes here. But you get the idea of this, right? You're taking that highest term.
What's the highest term and the second to the last one?
Second to last one.
The one with all the decimal places.
Oh, with all the decimal places?
Like, is it 300 n?
So in this case, it's n times log n. And we'll talk about this more. N log n is a a special kind of class of algorithms that actually, we end up seeing it a lot. Things take in log n time, so much so that we've broken it out as its own kind of category. So between n squared and n log n. And that'll become obvious when we start to do things like binary search trees, things essentially where we divide in twos, which we do a lot, right? That's where that log comes from. So some common complexity classes. Order 1 is how we say constant time. All the others is how we notate them. It's very straightforward. These are a few of the common classes. I encourage you to go to Wikipedia and look up complexity classes. There is a table, and it's beautiful, and it's full of all kinds of interesting classes that you don't really ever come across. But people researching algorithms and still pushing a lot of these hard problems forward, there are things in between these bigger categories that are still interesting. But these are generally the categories that we'll care about a lot. And so just to remind you why this matters quite a bit, here we've got, let's say, our big O, our worst case efficiencies, and here's our input sizes, right? So everything is pretty much okay at n equals 10, but you can see that things escalate pretty quickly, right? So I tried to get just like the keynote to just calculate this for me, and it just gave up on these two because it's very large. But so you could see how this would make a big difference if something you're processing jumps between these classes, right? And maybe not so if it's just a few elements, but definitely as you get higher and higher. So this is another example. I just want to kind of give you this trick if you don't know it already. If you're doing a big O analysis and you ever see nested for loops, right? We can use what's called the multiplicative property, and we can multiply those. So because this outer loop will happen, let's assume these arrays are the same size, n times, and this inner loop will happen n times. We can multiply those together, and we get n squared. So it's kind of a quick trick if you're ever asked to give a big O of some code, right? And you see some nice nested for loops, you can count those up and into whatever. Now, you've got to consider everything else that's in here. But this is just an example of a subset search. You've got two arrays, and you're answering the question, does one array contain the other array completely? And so you've got to do these double loops, right? You've got to loop through every element of the first array, and then for each of those elements, you've got to loop through every element of the second array. And so that becomes order n squared. So I'll give you a general taste for this notation that we're going to look at next time. This is kind of the formal big O definition. And we'll look at it visually first next time with some graphs because it's really intuitive. But there is a nice formal definition here. And it's essentially, we can say that a function is of an order. In this case, we'll say the function is f of n and the order is g of n. If we can find these constants that satisfy this inequality. And so if you want an example of that, we can say if we have something that's like 2n plus 10, we know that's order of n. And if we want to prove that, we can choose these constants will work for that, right? And so if you want to see how that breaks down, you can work it through and you can show it. Pretty much everything we do in class and definitely everything we do in an exam will be intuitive enough that you won't need to do this. This is something you'll do in some of your other classes in more detail, but here we'll kind of leave it at the high level. All right, so that's everything I want to cover today. On Wednesday, we will pick back up and finish computational complexity. See you then.